when I was invited, I was asked to speak on models of mesoscopic brain activity. I'll do this. I'll speak about the virtual brain, but I also wanted to take advantage of this wonderful summer school that you have here and try to make some connections. I have seen that you had, for instance, this morning you had Nicolas Brunel speaking, Scott Kelso will speak later. So what I would like to do is try to tie a few concepts and start with a very conceptual slide. Well, a circle, yeah. Start with a very conceptual slide and talk a little bit on my perspective on model data and metric. And I will take this image and take it for guidance through some of the scientific work that I will present. Yeah. So model data and metric. What we are trying to do when we model, typically we are trying to understand some of the underlying mechanisms that are generating the data. Yeah? So we call this causality, the causal mechanisms that are the actual cause, the lawful behavior that we follow in order to get this type of data generated. That is in opposition to statistical inference. So we distinguish causal and statistical inference. On the one hand side, statistical inference, we try to infer structure that is in the data. And in causal inference, we are trying to infer structure in the sense of, from the perspective of a causal hypothesis. So you have to have a causal hypothesis, a statement about what is mechanistically causing the structure that is in the data. Very often we can call this a model, yeah, like this. And there will be different concepts I will be introducing. Now, I'm defining a model organized by its parameters, A and B. And there are certain relationships of parameters. Parameters typically do not change in time, or they change very slowly in time. And then we have entities that we call state variables that are describing the evolution, the temporal evolution of a state or a state vector. But at the moment, let's focus on the parameters here. The interplay between parameters and states or state variables, yeah, defines a causal hypothesis. A causal hypothesis can be expressed in many different ways as a differential equation, as an integral equation, and most of them you can express also as an implicit equation, something like a plus b squared. Here it's in terms of an explicit equation. So, but a squared plus b squared minus 1 equals 0. That's the same thing as written here. Yeah. So here in this toy example, the causal hypothesis is that there is a relationship between these parameters that defines a circle, some circular form. Yeah. Now, so that's my model, number one. Number two, I perform a measurement like this point here. Yeah. I measure some type of correlation. I extract it out of the data. It provides me with a point that I can, in one way or another, locate in this particular domain. Now I want to relate it to the model, yeah, which means I need to define a metric, yeah. And please recognize that this metric is another explicit step that you're performing. For instance, you can ask the question, this blue dot that I measured, what is the closest point on this model here that has the shortest distance between the measured point and all the points that are on this causal hypothesis, so the circle in this case. Yeah, I can measure this, then I can make another measurement and find the next closest point. In order to do this, I need to, I need to define some metric. Yeah, this could be the Euclidean distance between here and between there. And in the presence of noise, I will not only have one single point here, but if I perform this measurement multiple times, I will have multiple points here defined on the circle. And when I plot this on this axis B, what I will get is something like a distribution of the projections of the red points that have been identified by my metric here, projected on the B-axis, and they can give me this beautiful normal distribution that I then can fit. Yeah. So that would be a possible process. And in order to make an estimation of the parameters of the model, my causal hypothesis, as informed by the data, the blue dots here. This we refer to as model inversion. We are estimating the parameters of this model, wherever this model is coming from, yeah, and trying to inform this. Yeah, so we can do the same thing for this particular measurement and many other measurements. If my metric changes, here I represent it as an oval, the story may change. Yeah, so keep this in mind. Give you an example for this. For instance, what if we have a measurement that falls directly into this, rather than outside here, into this point here, yeah, right in the middle of the circle? It's perfectly valid. And then if I ask the question, what is the closest point on our model corresponding to this? If this is directly in the center of the circle, the answer would be many of these different points. So here we are running into a situation we are running into all the time. It's called degeneracy, or in the field of neuroscience, neurodegeneracy. If I then, for instance, make a projection on this axis here, A, of the clustering of the points, I will get something like a bimodal distribution, because all the points that are here projected down here will provide me with one peak here, and those points down there also. But for this, I would even have to sample all of them if I do this systematically. But I would get a bimodal distribution because the density of these points in this projection would be higher. So if I then were to make an approximation that is Gaussian in this form here through a normal distribution, as I did before, I would get a non-informative result. I can still do it. And very often, many of us do this by claiming we need to take an unbiased approach. And if I don't have information about this, I may assume a Gaussian distribution. But here in this case, it's simply wrong. So there are very many issues in here that are traps in terms of data analysis, model building, data interpretation, etc. That I would like to unpack together with you in the first few slides of this talk here. Key issues here are the following. We can have neurodegeneracy or degeneracy of parameters, yeah? And that is actually not the exception, but that's actually very common, especially in complex systems such as the brain. This is something we need to deal with. So we have parameter spaces on the one hand side. This is a parameterization of our model. So that's one space. And this type of surface, neurodegenerate surface, we refer to this as manifolds. So the distribution of the parameters. And then there is a second space, the so-called state space, that is spanned by the state variables. These are the variables that describe the temporal evolution of the system. And we have not spoken about this yet. I just pointed this out, that a representation of a state variable in the simplified picture is this point here. Yeah? Keep this in mind. Measurements, model with a capacity for degeneracy, metric, yeah? And then the appropriate interpretation. Yeah? What I pointed out here, Monte Carlo Markov chain methods or variational inference, these are methods that are actually, when we project the parameters onto an axis, ways of estimating these distribution. The most reliable one, but also the most difficult one to handle, is what we call a Monte Carlo Markov chain approach, where we're actually sampling the manifold itself. Yeah. Very difficult, but possible. Yeah, we are using these technologies also. But very often we are making a simplification, such as that we are saying, let's assume it's Gaussian. Yeah, in many of some cases it is often Gaussian. This, for instance, something that we do in DCM, yeah, dynamical causal modeling, yeah, because there we can actually, we don't need to sample this numerically, but we can actually invert this analytically. So it's a very fast approach. So that's a picture I wanted you to have in mind. And I would like to link it to contributions of another gentleman in the 50s, 60s. That's Edwin Janes, who has introduced us to the maximum information principle, a very deep principle, actually, that is linking the notion of uncertainty to probability. And in fact, I cited this from one of his papers. There is an unambiguous criterion for the amount of uncertainty that actually beautifully agrees with our intuition that a broad distribution represents more uncertainty than a sharp one. We then refer to this as a probability distribution. And this criterion that he actually spoke about there is actually Shannon's information criterion, which he based on 3 or 4 axioms, such as additivity of information that needs to be expressed in terms of the probability distribution. So axioms that we can agree upon in terms of what information means, and then express it as a criterion that has certain properties. And he came up with this particular expression. Yeah? And what Janes did is he then linked it to the underlying deterministic equations, now which I called earlier the model, so our causal hypothesis, that is actually putting structure into the data. Yeah, and when there is structure in the data generated by some deterministic processes, this is generating correlations. And this is our access in the real world actually to this information that is in the data. Yeah, all we can measure physically are correlations. Yeah, and these correlations are actually linked to some of the underlying constraints, which I called F here. Think of this F to be this A squared plus B squared equal 1, I wrote down earlier. Yeah, and then multiplied by the probability distribution summed over all states provides us with a measurement, the mean value, which is what we can actually measure. When we take this information criterion and say, if we take all the deterministic features into account that are present in the data, yeah, and can agree upon that there is absolutely nothing else in there, yeah, plus the degeneracies that we spoke about, we can minimize that information criterion and actually derive a explicit equation, analytical equation for the probability distribution, which takes this form. It's an exponential equation. Lambda 0 is a normalization factor, plus all the causal hypotheses, the models, the deterministic constraints. So these elements that provide structure, yeah, and change it from a flat distribution. Yeah, without these terms here, it would be a flat distribution. With these terms, the structure enters. Yeah, and then once we accept that, we can actually link this to the correlations, to the measurements, and then perform some analytical manipulations thereof. For instance, take derivatives of this with regard to the parameters. And then this is the Zustandssumme, the partition function. This is just a technicality. We can actually derive the force equations. If the system is in complete equilibrium, we obtain what we know as thermostatistics. Yeah. So we have a closed system, and we can actually derive from this equation, we can actually derive the forces such as the shear forces or pressure, and we derive some of the collective collective variables, yeah, that exist on this level of description. And then you can call them pressure or temperature. Yeah. Scott will talk to you later about this also from a perspective that is non-equilibrium. But here, this is just for context, thermostatistics. I want to emphasize the general nature of this way of thinking in the from the perspective of how we started off. And now let me simplify it again to the simplest of all possible scenarios. And then we complexify it slowly, step by step, approaching the brain, yeah, as a network of coupled neurons. What is the simplest scenario we can think of in this context? And that would be actually, we can put a deterministic structure in there, which if it's linear, what we have is a linear fixed point dynamics. A one-dimensional linear fixed point that happens to be stable. This is as simple as it can get. We can write this also in terms of a potential function, a gradient potential. I plotted this down here. We said one-dimensional system, so we have one variable, x. We have a fixed point. For this guy here, it's x equals 0, so we're here. And we said it's stable, so it's attractive. Further away, the force is bigger, yeah? And as a gradient system, I can actually write it as by means of a quadratic potential, yeah? X squared divided by half. This is a potential. And if I have the potential from the formula I showed you earlier, from the maximizing of the information in the sense of Janes, as we discussed earlier, this potential I can actually derive as I can plug it into the formula we derived and write down the potential function is minus x squared half, yeah. And this provides me with a Gaussian distribution, actually. I'm plotting it here. This is a normal distribution, Gaussian. And this provides us with a stationary probability distribution function of a linear system that has a stable fixed point. This is what we have here. And this is the underlying deterministic structure. Having understood this, I can go a step further. And I can actually now extend it and deal with two variables. Again, linear, epsilon x, epsilon y. And I can measure again the correlations. As I did in the previous case, I didn't say that. Here I can measure the correlations, the mean value and the second order momentum. All others are 0. I can do this for the higher dimensional system also. X squared. This should be y and y squared, my apologies. I can again compute the probability distribution function, which is represented here and plotted. And it's again quadratic and again Gaussian and normal. Yes, and the corresponding potential is represented here. And if these two systems are uncoupled, so no deterministic exchange, the cross correlation will be 0, which means the cross correlation term I have in here is 0, and the potential is fully symmetric. If I indeed add a coupling function, so 2 beta x in here, then you see this deformation in the probability distribution function, and the cross correlation becomes non-zero. Yeah, and now let me go. This is again understandable. It remains normal. Let me go one step further and allow me to write the full probability distribution function and write it in terms of its conditional probability resembling Bayes' theorem, where I have a probability distribution function for y times x of y, so the conditional probability, providing me with a joint probability distribution. That's a formal equivalence. When I do this, I can actually separate these two terms and isolate them and identify this term here, which is actually the coupling term that if Carl Friston were here, yeah, this is the one that is actually identical to the free energy, which is actually being minimized in the free energy principle. Yeah, and in this case, it's the exchange between the two subsystems resulting in a flow in the system. Yeah. Having said this, I connected it at least formally, to the notion of free energy in this point. Let me connect it back to neuroscience, because this is actually what we can do. When we go to neural mass systems, neural masses are population equations that are being derived from the application of mean field theory. This morning, you had some lectures on spiking neuron networks. Yeah, so action potentials are being fired, and they obey a particular statistics. When you have this, you can actually apply some statistical theorems. So compute the different momenta and derive so-called mean field equations that couple the momenta, and you can actually truncate these momenta. So you have lower order representations of these momenta. First momentum is typically mean field, second momentum is variance. Yeah, so you can actually derive reduced equations under the assumption of correlations between the individual spikes. Yeah, and so Nicolas Brunel, that spoke to you this morning, he has done a model which is called Brunel-Wang. Yeah, there is Janssen-Ritt equations, there is Wilson-Cowan equation, there is a very recent model that has been developed by Ernesto Montbrió in Barcelona with his colleagues that I actually represent here. All of them are two-dimensional, and they differ in terms of the assumptions, in terms of the spike correlations. Then depending on these assumptions, you can use different mathematical expressions and arrive at different forms. But typically you obtain a two-dimensional equation system, V and R, plotted here, R and V. And the differential equations you can always plot as flows. Yeah, so you have a flow, the trajectory follows and then goes to a fixed point. You have a fixed point here, a stable fixed point, or you follow this flow and it goes down. So this is spiral, another fixed point here. And here we have something which is called a separatrix. So like a threshold. 95% of all these equations have a form like this, typically upstate, oscillatory, stable fixed point, a spiral, and a downstate. So you have a separation. A simplified form thereof would be that you have a downstate, upstate, and you ignore the fact that this is oscillatory. And then you have actually almost essentially one-dimensional system that is represented here, X dot. I'm plotting this cube here, and you have only a one-dimensional system, one fixed point, another fixed point. This one separates this, and you can move it up and down. When you move this curve up, these 2 points approach and annihilate, and this lower fixed point, left fixed point, disappears. Yeah, you can actually make an approximation of this system by means of one-dimensional system. Yeah, what I can do now actually is I can take two of these one-dimensional systems and couple them. That's the one-dimensional system that I just showed you here. So a one-dimensional system is equivalent with bistability, captures most of the neural mass modeled systems you find in the literature. And now I couple two of them in the sense as I did it earlier with the probability distributions. I couple it through the standard couplings between neural populations. And then I have this type of dynamics here, X and Y. This here is where both systems are in the downstate. This here is where both systems, both populations are in the upstate. This one is X is in downstate and the other one is in upstate, and that's the inverse. I can plot in the flow and I have some separatrices here. Now I increase the coupling between them. Stable fixed point, stable fixed point, stable, stable. And you see the flow deforms a little bit. I increase the coupling even more. Yeah, and even more. If I couple it with the same strength, I have actually a full complete circle where all the trajectories are being attracted to. Here I have a full complete circle where the dynamics is determined by a fixed point, stable, stable, stable. Flows are being attracted, but the circular shape is already still here. Why am I showing this to you? I'm trying to convince you that actually out of very basic properties of neural populations, when we couple them, the flows that are very generic, these grid-like flows, are actually being morphed into invariant manifolds in the state space. Let me show it to you now as I did before with probability distributions and potentials. This is a potential, the identical system I just showed you. Low coupling, and then I increase the coupling strength and it becomes circular. It becomes a invariant manifold that is degenerate. I'm linking back to the language I showed you earlier. Degenerate manifold, all the states are degenerate here. And here the manifold, the circular manifold is attractive, but these states here still express themselves. And in terms of probability distribution functions, this is what it looks like. So I can still deal with this system composed of two brain regional populations composed of neurons exactly as I did before. I can split it in terms of base, yeah, and actually write the probability distribution function and split it in a conditional probability distribution and the one for the state y, yeah. And then I can identify this one here formally as a free energy. And that's actually the term that is being minimized when you're trying to build a system and the brain is sampling the outside environment and is trying to minimize the free energy. So essentially going onto this representation, which is constructed by this flow defined on the manifold. Yeah, this is actually what this process of minimization of free energy means. Yeah. So, what is it I showed you in terms of two populations? When the system is non-linear, we are not just having Gaussian approximations, but we are actually having this type of, this type of structures that can take multimodal distributions. And that's very important to recognize, as we saw it in the first illustration. Effectively, multimodality is something we need to take, we need to consider. And when we build a network out of many different masses, neural masses or populations, we will get actually higher order structures. When we couple them, completely couple them, all-to-all coupling, symmetric coupling, we get these invariant manifolds in state space. And when we break the coupling, introduce an asymmetry, it is actually the asymmetry that generates a flow on the manifold that exists when I'm in the fully coupled, symmetrically coupled state. And this asymmetry actually expresses itself as a flow that is obtained when minimizing the free energy in the sense of Carl-Friston. So that was a little detailed and lengthy, but I think it's important that you hear this once, because you are actually now piecing different elements of the puzzle together from different perspectives that you'll overhear a lot in theoretical neuroscience. Let me show this to you in one more toy system, and then we go actually into the real brain. Yeah. So this is again 2 dimensions, yeah, x and y. And this is a fully coupled, symmetrically coupled case. As I showed you, it generates a spherical, or in this case 2D circular manifolds. There is no flow on it. I perform some symmetry breaking, and I break the symmetry, and then we call this actually null clients. X dot equals 0 and y dot equals 0. Each of them provides a circular structure in here. If they don't overlap, I'm having intersections, which generates actually a fixed point here, another one there. And then I have the flow that goes along the manifold to this stable fixed point here, away from the unstable one. And this is actually what you see now in the simulations. Here you don't have only 2 intersections, but actually 1, 2, 3, 4, 5, 6 intersections, generating in red stable fixed points and in black unstable fixed points. It's exactly this system here, composed of 2 units, x1 and x2, xi1 and xi2, plus a symmetry breaking. Here you see the corresponding time series. So in the simulation, you see it goes down. It travels on the manifold, and it stays on the manifold 99% of the time because that's a fast dynamics. Hermann Harkin, Aaron mentioned earlier, referred to this as timescale separation and enslaving. And most of the time, you're on this manifold here that is actually dominated by the slow variables, the so-called order parameters. And when you're having presence of noise, and that's the other thing I wanted you to realize, when in the presence of noise, the system is actually 99% of the time, it's sampling the order parameter manifold. So the slow dynamics reduced to a low dimensional subspace. Well, in this case, we have a reduction from 2D to 1D, yeah, but it's sampling the shape of this manifold. Here we are in state space, but the concepts hold as in the other case. Here we are in a 20-dimensional system, same story, but N here in this case, this was simulation performed by R.J. Pillai, my former PhD student, 20-dimensional system, and he let it collapse on a sphere. So a sphere is a 2-dimensional manifold spanned in a 20-dimensional space. We are visualizing it only 3-dimensionally here. Dynamics goes down, driven by noise, hangs out on a fixed point, and then he kicked and the system went into the other bistable fixed point. Yeah. So this was the dynamics that was generated here. So here the situation becomes less trivial and less obvious anymore, but all the concepts hold and prevail and scale up actually to very high dimensions. And this is actually important for today's talk, but also for the talk later when Scott Kelso will talk to you about behavior. He's actually one of the leading researchers who has established the field of coordination dynamics. And this is essentially in behavior, we are pursuing the idea and the theory that there is an emergence of low dimensional structures that are actually capable of performing meaningful dynamic function, not just emergence of a state, but actually trajectories that follow a flow on a low dimensional object. Let's call it a structured flow in a manifold. That's what we refer to it. Hermann Harkin in the 80s, he developed it in the theory of synergetics. What he applied is a mechanism of proximity to bifurcations, employing a theorem which we call the center manifold theorem. So when you're close to a phase transition, to transition from one behavior to the other, you have this reduction to low dimensional manifolds. Yeah? What we did here with structural flows on manifolds, we actually linked it to the principle of symmetry breaking in the topology of a network. And when you're close to a fully symmetric situation, like all-to-all coupling, yeah, you can actually generate these low-dimensional subspaces in which the dynamics evolves. Yeah, it's attractive, and you can actually control it. So that is not just locally determined as in the synergetic case, but it's a generalization thereof. Yeah, and that's I think it's correct to say that this is what Scott Kelso was after. Now, that was the theoretical framework. Let me use this in the remaining time. Let me make some use of this and carry it into applications. So we talked about the virtual brain was mentioned earlier. What we did in the context of the virtual brain is build a simulator that is actually taking the connectivity directly from the individual, him or herself, and is generating the network topology, including all the symmetry breaking, the structural features, and is actually biasing the network to this particular topology. We use the MRI for that. We use tractography to extract the information directly from the individual. And then we actually developed workflows that allow us to link these things up. From the MRI, we can extract the brain topography, so the cortical and subcortical surfaces, and parcellate it. Then we get the network nodes as you see here. And when we once we parcellate it, we can actually extract from diffusion tensor based imaging the fibers by performing tractography and actually assign the different fiber tracts to the individual parcels. So we extract so-called streamlines perform the tractography on it, and develop what is actually the topology of the network, the connectivity. When we put this together in the same reference framework, so topography and topology, we can span it in three-dimensional physical space, and we have a network. And what we need to do then is to equip it with mathematics. And the mathematics we just spoke about, the model, this is the causal hypothesis in a causal inference framework. Yeah, this is a dynamic system with a network node. This would correspond to the bistable system I referred to earlier. And then the connection connectome, connecting the individual nodes in the network. In a fully connected system, that would provide us with these spherical manifolds in the high dimensional state space, and then we obtain symmetry breaking through the connectome. So, en résumé, we can put these things together, connect it, and the advantage of this using only structural data to build this is we have a network where we can actually plug in sensors afterwards. Yeah, so which means we are not using the functional brain imaging data to build the network, but we are actually using the functional imaging data to constrain the network. This I will talk about epilepsy, SEG here, but it can be done for MEG, functional MRI, any type of brain imaging. I invite you to check out our virtual brain platform where we put all the workflows together. So you don't have to do it. You can process the connectome. You can perform some reconstruction of the connectivity. You can define your neural mass model on the network node and then run the simulator. Here's the website, by the way. It's all free. It's an open source platform. It's a community project. Yeah, and you can run simulations here either on the source space or on the sensor space. So this is an example of EG, and you can connect directly to EBRAINS and run it on the high performance computing clusters that are available in EBRAINS, which is a European digital research, neuroscience research infrastructure. So with this tool and the concept of structured flows on manifolds, we can now do actually science. The concept provides us a vision, yeah, the way of asking questions, defining metrics that are appropriate for this type of questions. The virtual brain provides us with the tools to do this, yeah. And I'd like to, in the remaining time, to apply this to epilepsy, in particular to the application that we have developed here. Yeah? And there we have developed a model-based approach towards epilepsy. Epilepsy is a disease. Yeah, it's a disorder, in fact. Yeah, 1% of the population suffers from that. And 30% of all the patients, they are drug resistant, which means you cannot treat their epilepsy through medication. You need to do it through different means. And the standard means is actually surgery. In order to perform surgery, you need to know where to perform surgery. Yeah. So what we do, this is a technique that has been developed by Jean Banco, Jean Talarac in Paris in the 60s and is becoming a standard. You introduce needles about 10, 15 centimeters long with 10, 15 or 20 contacts. Here you have the spacing on these needles into the brain. Between 5 to 20 needles. That's the maximum I've ever seen, 20 needles. Each of them has the number of contacts. It's called stereotactic because you measure inside in the volume. As opposed to grids, you can have also grids that you slap directly onto the cortical surface. And then you measure this type of activity here. Yeah? And based on this type of activity, you have to actually to infer where to perform the resection in the brain. In terms of surgery success, 60 to 70% success, in particular in temporal lobe epilepsy, extra temporal lobe epilepsy, the surgery success goes down all the way to 25% in frontal lobes epilepsies. Yeah, has not changed over the last 50 years. This tells you something. So, meaning there is a lot to discover what we need to learn. That's our workflow of how we work with the virtual brain and the concepts I just presented to you. We build out of the non-invasive imaging a personalized brain avatar, personalized, so data-driven in the sense that we use the individual's data to constrain the model. We equip it with mathematics, this general network, and we are able to run the dynamics. Actually, we can refine the network model. And what we do in order to render it even more individualized is we apply methods of Bayesian inference. So data fitting, estimating the parameters in order to identify, and the parameters for us are the epileptogenicity. Yeah? And those we want to estimate and then extract and go to the surgery and extract them. Remember my first slide, model inversion? We are estimating parameters. If the parameters are degenerate, we better know that they are degenerate, hence because there are multiple options. If they are non-unique, yeah, the surgeon has to do a unique resection. Yeah, there are no alternatives. So it's a highly invasive procedure. Neurodegeneracy is not optional. It's a piece of knowledge you have to have. Yeah. Once you understand this, is what is actually our target of the sampling then? Yeah. Yeah. What do we want to sample? Or in other words, in the context of the storyline I told you in the beginning, what is a structured flow of manifold that is, in the case of epilepsy, sampled or expressed by the evolving brain before, during, and after a seizure, because that's our object that we want to sample, from which then, in the presence of a causal model, we wish to estimate the parameters that will be somehow representative of the brain regions that the surgeon will resect. I'm slowly trying to close the loop. Yeah. There we have used lots of mathematics, actually, and in this case we have used deep nonlinear dynamics, and I don't have the time to go into this. I just want you to understand the essence. Yeah, these are experimental data. This is coming from a rat in hippocampus, in tuto hippocampus. Yeah, this is roughly 10 minutes. This is one seizure, about 2 minutes. This is seconds that is plotted here. Pre-ictal stage, discharge, post-ictal, pre-ictal, ictal. Yeah, we can actually illustrate this mathematically as what we call a fast, slow system. Discharges, slow discharges. And there we can go back to the mathematics that we're familiar with and actually say this has to be described, must be described very fundamentally by theorems linked to fast, slow systems. And there we can start invoking the language of slow manifolds and fast manifolds. I don't have time to enter into this, but what I can tell you, a mathematical object that is being represented like this has the corresponding unfolding in a three-dimensional state space. You have the slow manifold that corresponds to the resting state. Then it destabilizes and it goes into a fast oscillatory state. And then it leaves it and goes back here. The exit bifurcation we call seizure offset. This is seizure onset. And this is the resting, the healthy physiological state. And this is a pathological ictal state. This is a mathematical object that is our interest. This is the structured flow on manifold. And these objects can be actually characterized by how you leave the rest in order to go into the ictal state and back again. And this is called bifurcation theory. And there is only a finite number of ways of doing this. I'm referring to these papers here. Take a screenshot and have a look at them. And a good thing about this is because there is a finite number of ways how to go into such a seizure or exit it, we can actually characterize it by different type of amplitude and frequency behavior. For instance, here in this example, the frequency does not change and you have a baseline shift. We call this a saddle node bifurcation, whereas here for the half bifurcation, it's central and the amplitude increases, but the frequency remains fixed. Whereas this one is, where is the homoclinic one? The homoclinic one is this one here. You cannot see it. It becomes slowing down. It goes logarithmic. So we can actually characterize it, put it into a taxonomy of onset and offset bifurcations, and build seizure taxonomy, like the periodic table of chemical elements with different properties. we can do the same thing here. We call this Dynamo Types and build different seizure classes. Yeah, and here you have examples for from experimental data. I really recommend this paper here, where this mathematics has actually been applied to characterize different types of seizure types. Let's look at this one here. That's a saddle node offset that I told you about. Saddle node. This is what it looks like in the model. And this is a corresponding flow changes. You have a fixed point here that collides with a separatrix point. They approach each other, collide, and it becomes a circle. Yeah, this has these properties here with an off-limit cycle offset. Yeah, so you can do this, and it turns out that actually there are only, out of the 16 possible classes, yeah, there are only 2 or 3 dominant classes which describe all the different dynamo types. This is the mathematics that we can now use. We can build these structured flows on manifolds and actually sample them with the techniques I was telling you about. Yeah, this is a structured flow for applications in epilepsy. I need to simplify that because this is still, with all the clinical variability that we have, this is still too difficult to sample with the technique. So we project it in 2D. This is a healthy state, rest state, and this is a discharge state. These are the points that we measure. This is essentially the envelope of the discharge, yeah, projected down here. And this is the structure that we sample then mathematically against the data. And these are experimental data, I can tell you here. Yeah, so here, this area, these are different brain areas, node 1, node 2, etc. So this one discharges, these 2 don't. Yeah, and when we do this, you recognize these pictures earlier. Yeah, actually, these are empirical data. Yeah, where we extract now the parameters. Yeah, and extract the parameters for an epileptic brain across all the nodes, in this case, 164 brain nodes, and we estimate the excitability here. When it's very high up, it's epileptogenic, meaning target for the surgeon. When it's low, it's healthy. Let me zoom into some of these here and plot them here. These are different brain areas. And you see some are multimodal, others are not. This is a neurodegeneracy we need to know about. Yeah. And this figure here corresponds to this one. Yeah. If you do a variational inference assuming a Gaussian normal form, then you're implicitly assuming linearity of your system. If your model that you use for the construction is nonlinear or not, it does not matter. If you make a normal distribution approximation, you assume linearity and you try to fit this type of behavior, and you miss the multimodality here. Yeah. If I take this one together with this one and another area, and I span it here, this is hippocampus, for instance. Yeah. This other area and other area, I get 3 different options, rather than if I had done variational inference, I would get only one single option. This is very important to know in real world applications. And I'm coming to the end, because this is what we do. We estimate these parameters, we represent them here, and then provide this information to the surgeon. And this is after surgery, post-surgical MRI. This is the type of intervention that is being done. Yeah. We can use this now to run simulations. And on the source level, project on the electrode level and simulate patient-specific individual seizures. We can interfere, we can simulate different resections, we can stimulate, use brain stimulation to stop seizures. Yeah, we are running currently a clinical trial where this technology is being systematically evaluated. We are halfway, in fact. Yeah, 13 reference centers are using this, a sampling of the so-called epileptor manifold. After virtualization of the patient, all the data being centralized. We build those in Marseille. We provide it in a clinical report and feed it back to the decision-making staff that then decides surgery or not surgery. Yeah. So we are halfway. So we started in June 2019. We are halfway in 2023. The trial is going to be finished, but we already have first results. This last thing I'm going to share with you is The results, what we can do is we reconstruct the data, and we can either compare it against post-surgical MRI, that's this leg, or we can compare it against clinical hypothesis. If we compare it against post-surgical MRI, we can actually split it into seizure-free patients and non-seizure-free patients, and then look at what the clinician thought would be. And this is VP, virtual epileptic patient, us. So the precision, which is equivalent to specificity, a statistical classification metric, we're doing pretty well. And it jumps down, so it falls down when the patients are non-seizure free, which is actually good, implying that there is some causality in the system. Yeah, but this is still retrospective. Or if we compare the seizure-free versus non-seizure-free patients in terms of the distance between what the virtual brain predicted and what the clinicians actually did, is represented here. I need to stop here. Yeah, I still have a few slides in terms of an outlook, but I prefer to have maybe time for questions and comments if you have anything from your side. So I stop here at this point and go to a very important slide at the end, which is my colleagues and friends that do all the work with me. Yeah, in particular Fabrice and Maxime, which are part of the clinical team. Yeah, thank you.